Hello guys, welcome to another video from Computer channel. In this video we're going to solve the sixth problem in Sipser textbook actually, and in this question we have some expression and we must construct a DFA for all of them, and that's it. Let's solve it together. So this is the sixth problem. It says that give a state diagram of DFAs recognizing the following languages. In all parts the alphabet is 0 and 1s. Actually I write every part in my notebooks, so let's solve them. The first part A, is that W begins with 1 and ends with a 0 actually. So if you want to construct a DFA for these languages, we know that the regular languages that DFA recognize them are closed under the intersection. So we can first construct a DFA for languages that begin with a 1 and then construct a DFA for languages that ends with a 0, and after that construct a DFA for intersection of these languages. So let's solve it actually. We will divide our languages to two parts actually, L1 and L2. L1 says that W begins with a 1, and L2 says that W ends with a 0 actually. So let's construct a DFA for L1 first. For L1 we have actually W begins with a 1, sorry, so it will become like this. That begins with a 1. We have this transition functions here, and this is our actual state actually, and after that it's not important, so it will be like this and like this. So this is the DFA for L1. For L2, here we have W must ends with a 0, so it will become like this, ends with a 0. So if we have this transition here and this is our actual state, if we see 1 0 we will say here, and if we see 1 we will back to our first state here, and we have another transition here for 1. And actually this is the DFA for the languages that ends with a 0. And now let's construct a DFA for intersection of L1 and L2. Actually I will construct a DFA that is somehow the optimized form of the DFA for L1, intersection of L1 and L2. For intersection of L1 and L2, and this is like this actually. If we see 1 and if we see 0, we know that if we start with 0 we will never reach our actual state because W must begins with a 0. So that's it for a start with a 0. But if we start with a 1 we will continue, and it will be like this actually here, 0 and 1 here, and this is our only actual state actually here. If you notice to these parts, you know that in here actually, let me show you, we will start with a 1 here, and if we see 1 0 actually we have a chance that our string might end with a 0, and after that if we see other 0 it is not important actually, because we actually have a chance to end our string with a 0, so we will stay here. But if we see 1 we will back to our last state here, and we will wait for 1 zeros that make a chance for us to end our string with a 0. And that's it. This is the DFA for intersection of L1 and L2, or better I say for language L. So that was part A. Let's go to part B here. For part B we must construct a DFA for L language that says that W contains at least 3 A's. And this is so simple actually. Sorry for this here. Let's construct it together. Actually here the number of 0 is not important. So every time that we see 1 0 we will stay in our state, and if we see if we see a 1 we will go to our next state, so it will become like this. And this transition, and if you notice here we have we reached 3 1, so this is our actual state, and after that the number of 0 and 1 does not matter actually, and we will stay here. And yes, that's it. This is the DFA for language L here. That was for part B. Let's go to part C. For part C says that W contains the substring 0 1 0 1, or better says that W is equal to X 0 1 0 1 Y for some X and Y. So actually this is simple. You just have to notice that we have a chance to start with 1 or 0, and we must follow the pattern. So actually if we see 1 we will stay here, and if we see a 0 we might have a chance to start our pattern that is 1 0 1 0 1 0 1. And here we have transition here for 0, actually 0, and after that 1, and after that another 0, and finally another 1. And if you notice here we see 0 1 0 1, and this state might be our actual state here. So after that if we see other zeros or 1, actually this is equal to Y. That's the question, notice that. But in middle of our DFA, actually here, if we see 1 0 we must back to this state, and here if we see just 1 1 we might back to this state here. So yes, that's it. We have our pattern actually 0 1 0 1, and in some these states if we see actually better says some other alphabet than compared to what we expected, we will back to our previous states. So yes, that's it. This is the DFA for part C. Let's get to part D. Part D says that W is equal to the language that W has the length at least 3 and its third symbol is 0. Actually here we have a trick. So if you notice that here if we name this part, we know that we can write the L like intersection of L1 and L2, and the first part is our L1 and the second part is our L2. So we can write it actually like this one, intersection of L1 and L2. And if you notice that we can actually define that L2, or better I said actually L1 is a subset of L2, because if we want our third symbol must be a 0, we must have a string with at least length of 3. So that's it actually. L1 is a subset of L2, and we know that if we have this actually part, the intersection of L1 and L2 is equal to L1 actually. And yes, that's it, I think so. But wait. Oh, I make a mistake actually. The L2 is a subset of L1 because every string that their length is at least 3 is a actually superset of the string that their third symbol is 0. So actually L2 is a subset of L1 and the intersection of them is equal to L2. And yeah, that's it. We must construct the DFA just for L2. This makes our work so simple, if you notice. So it will become like this for L2, or better I says that the intersection of L1 and L2, we have a DFA like this. Here first, then it doesn't matter that we start with a 1 or 0, so our transition is like this. For the next state also it doesn't matter, so it will be like this. But in this part, when we want to write our third symbol, if we write as 0 here, we reach our active state, and after that the number of 0 and 1 does not matter actually. So this is our active state, but if we choose 1, we will never reach our active state because our third symbol in this condition is 1, and this is not true. So yes, that's it. This is the DFA for intersection of L1 and L2, or better says that L2. So that was part D actually. Let's go to part E. Part E says that W starts with 0 and has odd lengths, or starts with 1 and has even lengths. If you want, we know that the regular languages are closed under union and intersection. So we can first write a DFA for this part, and after that write a DFA for this part. Actually, we call this part L1 and this part L2, and after that write a, or better I say, construct a DFA for union of L1 and L2. Actually, so, but actually I choose that to construct the final DFA for you because it is so simple. I know that this expression is so harsh, but if you want to construct the DFA, it becomes so simple for you. Actually, first, we must choose between our string starts with 0 or our string starts with 1. So it will become like this here. Actually, for L here, not L1 or L2. For L, it will become like this if we start with a 1 or start with a 0. So if we start with a 1, our condition is that actually our lengths must be even. So after that we have this transition for that our lengths become even actually here, and this is our active state. And you know that we just constructed DFA for even lengths, but if we start with a 0, our lengths must be odd. So here we constructed DFA for odd lengths, and it will become like this. And that's it. This is our these two states here and here. They are our active states, and that's it. Actually, that was so simple, but the expression was so hard. And that was for part E. Let's go for next part actually. Part F. Part F says that our language is W, that W does not contain the substring 110. We know that the regular languages are closed under complement. So the regular languages, so if L is regular, then L complement is regular too. And that's it. we must actually change the started states with the normal states, or better I say replace the normal state with accepted states and replace the accepted states with normal states. So first, we construct a DFA for L complement, and it will become like that W does contain the substring 110. And now let's construct a DFA for L complement actually, and it will become like this. First, we know that if we start with a 0, it doesn't matter. Our pattern is that we must have 1 first, so we have transition for 0 here, and after that if we see a 1 we will go to this state, but after that if we see a 0 we just break our pattern, so we will back to our first state here. But if we see another 1 we will reach our next state, that is here, and after that if we see a 1 actually we don't break our pattern, because we know that actually this string 1110 has the 110 as its substring. So if we see just another 1 we will stay here like this, and after that after that if we see another 0 we will reach our accepted state, and after that the number of 1 and 0 does not matter actually, so it will become like this, and this is our accepted state. But that was a DFA for L complement. We must draw the DFA for L. We actually we have to actually replace the normal state with accepted state and accepted states with normal state, so it will become like this for L. And we have all of our transitions, actually 1 0 and another 1 here and another 1, and finally 0 and 1 and 0, and our accepted states are these 3 states, and that's it. This is the DFA for L, and this is our answer. So let's go for next part. The next part is part G. L is equal to W, that's the length of W is at most 5. Actually this is so simple, we must check that our lengths go over 5 or not. So we know that the empty string is lower than 5, so this is accept, and in every transition we have 0 and 1, because if we use both of them it will increase our length, so we can use from both of them. And actually this is accept, and another 1, this is accept because we reach length of 2 here, and after that this is accept 2, and this is accept 2, and this is accept 2, because here we reach our 5 lengths. That is our accept condition here. If you notice, this is lengths of 0 and 1, 2, 3, 4, 5. But after that, if we see another 1 and 0, we will actually go over our condition, and we will never reach our accept state. So it will become like this. And that's it. This is the DFA for language in part G. Yes. So now actually let's go for next part. The next part, this is part H. Part H says that W is any string except 1 1 and 1 1 1. Oh, so if you want to construct DFA for this one, it will become like this. We know that the empty string is our accept state, so this is our accept. After that, if we see a 1, uh, we also accept this because this is not in our accept patterns. So this is accept. And after that, if we see another 1, we reach one of our accept states. So this is not our accept state, and after that another one. This is like the previous one. So, but what about zeros? We know that if we see just 1 0, we break our pattern and we will never reach 1 1 or 1 1 1. So in every part, if we see a 0, we reach our we actually break our conditions and reach our accept states. So this is something like this, that this transition are 0, but the final one, actually this transition is 0 and 1, because if you notice that after this part here, actually we will go over 3 1, and we can see a string like 4 1, or 5 number of ones. So, and all of them are our accept states. So actually our final transition is like this, 0 and 1, and in this state the number of 0 and 1 after that does not matter. So this is our accept states too. And that was the DFA for part H. Let's go for next part. The next part is part I. Part I says that our language is W, that every actually odd position of W is a 1. And this is so simple. But let me tell you something. I think that this expression has some ambiguous, because we don't know that the empty string is accept here or not, because we don't have any information about its odd position. So actually I construct 2 DFA for you for both condition. If we accept the empty string, or better I say epsilon, our DFA will become like this actually. And we know that if we see 0, we will reach one state that is not our accept state, like this. But if we see a 1, we can reach our accept state, and after that if we see 1 and 0, it does not matter. Actually it does matter, but it doesn't matter in our pattern, so we will back to our previous state. And this is like this. But if we don't accept the epsilon, our DFA will become like this. Again, we have this transition for zeros and this state. But if we see a 1 here, actually this is our accept state here, and after that if we see a 0 and 1, this is accept 2, and if we see 1 here, we will back to this state. But if we see 0 here, we will go to this state that is not our accept state, and it will become like this actually. And actually, or better says that it will become like this. Yes, this one is better, because I just define one more state, that the 0 transition will go there, and after that the number of 0 or 1, it does not matter, because we will never reach our accept state. And that was the DFA for part I. Actually, let's go for next part, for part J. For part J says that our language is W, that actually W contains at least 2 zeros and at most 1 ones. Let's break this to two part actually. This part will become our L1, and this part will become our L2. Yes, so L1 is that W contains at least 2 zeros, and L2 is equal to W, that W contains at most 1, and it will become like this. So first let's construct the DFA for L1. Actually, this is L2. For L1, we know that W must contain at least 2 zeros, so it will become like this. We know that here the number of 1 does not matter, so actually it will become like this, 1, and after that 0, again this transition for 1 and another transition for 0. Here we reach our condition, and after that the number of 1 or 0 does not matter. And actually this is the DFA for L1. For L2, actually we have this DFA. Actually W must contain at most 1 actually, so it will become, we know that here the number of 0 does not matter, so we have this transition for 0, and we know that the epsilon is our accept state, so this is accept, and if we see another one, this is also our accept state. Again, the number of 0 does not matter, but after that if we see another one, we reach another state that is not our accept state, and after that we will never reach our accept state, so it will become like this. Yes, that's it for L2. And finally we must construct a DFA for intersection of L1 and L2 actually, so it will become like this here. We know that if we want to construct a DFA for intersection of L1 and L2, actually the number of states is Cartesian product of L1 and L2, that is here is 3.3, and it is equal to 9 actually, so we must have 9 states, so it will become actually like this. We have this transition for zeros in every part, and these transitions for 1 again in every part, so we construct this and this, again another transition for 1 here and here and here, and yes, and that's it for 0 and 0, and after that number of 1 does not matter, and we have this transition for 1 and 0 here, and another transition for 0 here and here. And we know that first let's actually show the acceptable state for L1 in this DFA. The acceptable states for L1 are those that contains at least 2 zeros. So if I want to show you these states, actually here are our acceptable states for L1. But for L2 says that will contain at most 1. So, and we know that the acceptable states are actually, let me see again, will contains at most 1. So are these, and this part are our acceptable states for L2, and intersection of them are these 2 parts. So yes, this is the DFA for intersection of L1 and L2. That was for part J. Let's go to next part. The next part is so simple actually. We must construct a DFA for L that's just accept epsilon or just 1, 0. So yes, that is so simple, and it will become like this. If I want to show you for L, we know that if we accept epsilon, our starter state is our accepted state. So it is like this here. And after that, if we see a 0, we reach our another accepted state here. But at first, if we see a 1, we reach another state that is not our accepted state. And we just actually define this transition for 1 and 0 here. And after that, 0 or 1 does not matter. So yes, this is the DFA for K. It is actually accepts epsilon in here and accepts 0 in here. And yes, that's it. That was the DFA for part K. Let's go for parts actually L here. For part L says that W contains an even number of zeros or contain exactly 2 ones. So if I want to, again we break the language into 2 parts here for L1 and here for L2, and we know that the regular languages are closed under unions. So finally we construct the DFA for union of L1 and L2. So let's begin here. L1 is actually W, that W contains an even number of zeros. Yes. And for L2 we have this part says that W contains exactly 2 ones. So yes, this is for L2. First, let's construct the DFA for L1. For L1, we have this DFA that is so simple. We must accept a string that contains even number of zeros, so it will become like this. We know that the epsilon is our accept state, so it will become actually like this. We have this transition for 0 because the number of 0 is what matters for us, and the number of ones does not matter for us. So we have these transitions here for 1. And yes, this is the DFA for L1. For L2, actually, for L2 L2 says that will contain exactly 2 ones. And again, here the number of 0 does not matter, so it will become like this. We have these transitions for 1 that if you see just actually some number of ones, we will go our next state until we reach 2 ones. So here I reached 2 ones, so this is our accept state. But after that, if we see just another number of ones, I go to this state, and this is not our accept state, and it will become like this. And in every part we have this transition for 0 because the number of 0 does not matter. So yes, this is a DFA for L2. Now let's construct the DFA for intersection of L1 and L2. Actually, I'm sorry, for union of L1 and L2. Actually here again, the number of states is the Cartesian product of L1, number of states in L1 and L2, and here 2 times actually 2.4 is equal to 8, so we must construct the DFA with 8 states, so it will become actually like this. Here we have this transition for 1 again. Yes. And in every part, if we see 0, we will go to this part and back to our previous state. So yes, it will become like this and this, and we have this transition for 0 here and another for 0 here, again for 0 here and here, and it will become like this, and we have this transition for 1. So this is our DFA. Now we must show the accepted states. We know that for L1 our accepted states are those that we have an even number of zeros. So if I want to show you them, these are our accepted states for L1, yes. And for L2 says that W contains exactly 2 ones. So so these 2 states are our accepted state for L2. And we know that for union, we actually accept all of these states, because in intersection we must actually select those that are in accepted states of L1 and in accepted states of L2. But in union, we just accept all of the accepted states in L1 and L2. So all of these states are our accepted state. And yes, I just forget some transitions here. Yes, here and here. And yes, this is the DFA for union of L1 and L2. Let's go to the next part. Next part, actually this one is so important. That the language is the empty set. So Betroy says that our language is like this. Actually, we don't accept any string. So our DFA will become like this. We just have one state and we don't accept any transition. And yes, this is so simple. Because actually when our language is the empty set, we won't actually accept any string. So we won't actually accept any transition here. So yes, that's it. This is for part M. For next part, actually I think this is the final part. For final part, we have all string except the empty string. So actually this one is so simple. I'll show you, because if we accept the empty string, actually we accept the epsilon. So our starter state is our accepted state. So all we have to do is add another state to our empty string and choose that one as our accept state. So it will become like this. Yes, that's it. This is the DFA for all the string except the empty string. Because if we accept the empty string, or better say epsilon, our starter state in here will become our accepted state. And yes, that's it. So finally we finished the question and solved every part. I hope you guys enjoyed this video. Actually, if you have any idea or opinion for us, just leave a comment for me. I will read all of them. And if you like this video, like it and subscribe to my channel. This is, I don't know how to say that. I really become so happy if you subscribe to my channel. And yes, that's it. Have a nice day, guys. Goodbye.